So today we're going to talk about free fall. Actually, a lot of times people think about like skydiving or jumping out of a plane when they think of free fall. But free fall is an object is in free fall when the only force acting on it is gravity. So when you are parachuting or when you're falling off of a plane, there's air resistance. So that's actually technically not free fall. So the only force acting on it is gravity. So we are not thinking about air resistance or anything like that. Just something I wanted to clarify. So let's look at this conceptual question. How does the time of the ball on its way up compare to on its way down? Where is the speed of the ball the fastest? Where is the speed of the ball the slowest? If there is air resistance, which way does it take longer? And where is it going the fastest? So anyway, if you want to pause and try on your own first before looking at my explanation, I highly recommend to do that. But if not, here we go. So it's going to take the same amount of time going up as it takes going down. Same amount of time, so same time. Where is the speed of the ball the fastest? So if you were throwing it here and it comes back here, it's going to have the same exact speed. So if you throw at, like, let's say 10 meters per second, right here, it's also going to be negative 10 meters per second. It's actually exactly parallel. Wherever it's moving on one side, it's going to be moving at the exact opposite. So if it's like 3 meters per second here, on the opposite side, it's negative 3 meters per second. So the point in which it is released and when it comes back to that height. Where is the speed of the ball the slowest? As you guys can imagine, it's going to be the slowest at the very top. It's actually just, for a moment, it doesn't move. 0 meters per second. If there is air resistance, which way does it take longer? And where is it going the fastest? So this is an interesting question, probably hard to a little bit think about. But what's happening is if you throw this really quickly at the beginning, what's going to happen is it's going to dramatically start to decrease because both gravity and air resistance are acting against it a lot. Especially air resistance is strong right from the beginning because it's moving quickly at the beginning. So when it comes back down and it reaches this point, it's not going to be going as fast as 10 meters per second. It's going to be a bit slower. So where is it going the fastest? It's going to be going the fastest the moment it's thrown. Okay, so if it's going faster on this side at the beginning, that means it's going to take longer to go all the way to the end over here. Okay, so going down is going to take longer, and the moment it is thrown, that is when it's going the fastest. All right, let's just kind of go through this. If I throw a ball downward, will the acceleration be greater than 9.8 meters per second squared or less than 9.8 meters per second squared? 9.8 meters. If I throw a ball up while the ball is initially traveling up, is the acceleration positive or negative? Explain. What would happen if the acceleration was positive? At the very top of the ball's motion, what is the ball's acceleration? Positive, negative, or 0? What would happen if the acceleration at the top was 0? And yes, just because velocity is 0, that does not mean acceleration is 0. Acceleration and velocity are different rates of measurement. So just letting you guys know, for all these answers, if the only thing acting on is gravity, it's always just going to be negative 9.8 meters per second squared. It's that for every single thing, okay? I don't care if it's thrown down, thrown up, thrown sideways, whatever is happening. If it's in the air and the only thing acting on is gravity, gravity is trying to pull it down negative 9.8 meters per second squared. I don't care if it's not moving. If it's in the air and we're on Earth, it's negative 9.8 meters per second squared. Also, what would happen if it was the acceleration pointing up? That means if you threw the ball, it'd be going up like a rocket ship going upwards. Okay, it's not slowing down. If the acceleration is up, then it's just going to keep going up. All right, moving on. Two objects are thrown from the top of a building. One is thrown up, and the other is thrown down, both with the same initial speed. Which object is moving faster when it hits the ground? Okay, so we have one object, we'll call this A, another object B. And let's say we both throw them at 3 meters per second, okay? And since this is going down, I'm going to call it negative 3 meters per second. So which object is moving faster when it hits the ground? So in the ground here, which one's going to go the fastest? So this is an interesting question. However, what you should know is that this ball A, when it comes back down at this point, it's also going to be going down at negative 3 meters per second at this point. So what that means is, when they hit the ground, they're both going to be hitting the ground at the exact same speed. Because even though you're throwing this up, when it comes back down to that same point, it's going to be going the same speed it was thrown. So both will be the same. Two objects are dropped from a bridge 1 second apart from one another. As the time progresses, the difference in their speed, A increases, then stays constant, B decreases, then stays constant, C increases, D increases, E remains constant. Okay, so let's just draw this out. What happens is, okay, we drop a ball, and then, so the ball falls, and then 1 second later, we drop another ball. So we're going to call this the first ball that's dropped, and then the second ball that's dropped. And as they're both falling, the question is, what happens to their speed? So this one might be a little bit tricky. One thing that I just want to say is the acceleration is 9.8 meters per second squared, or you could think about it as 10 meters per second squared. Okay, maybe I do approximately 10 meters per second squared. What we should know is every second, both of these balls are getting 10 meters per second faster in the downward direction. So as time progresses, the difference in their speed remains constant. This first ball is always going to be 10 meters per second faster than this second ball. Okay, so they're both accelerating at the same rate, 10 meters per second squared, but since this one had a 1 second head start, that means this first ball is always going to be 10 meters per second faster than this second ball. Okay, it's a little bit confusing, so think about it a little bit more if you haven't really grasped it, but try for it to make sense. All right, final example. A space explorer on a different planet throws an object downward on a planet with an initial velocity of 2 meters per second from a height of 6 meters above the surface. The object hits the ground after 2 seconds. What is the acceleration due to gravity on this planet? All right, so let's draw this out quickly. We have an object. We throw it down 2 meters per second. This object goes down 6 meters and hits the ground after 2 seconds. So it hits the ground after 2 seconds. What is the acceleration? So we're looking for what the acceleration of gravity is on this planet. So let's see what we know. We know initial velocity is negative 2 meters per second because we throw it down. We know it's going to be falling down a displacement of negative 6 meters, and we have a time of 2 seconds. And what we're looking for, acceleration. So very good. Now we have 3 pieces of information, and we have the one that we're looking for. So whenever you have 3 pieces of the information in kinematics and the one you're looking for, you can solve the problem. So let's look at which equation we're going to use. And we should be using this one. The initial y, t plus 1/2 a t squared. I'm going to put ay. Okay, so displacement of y, negative 6. V initial, negative 2. Time, 2 plus 1/2 ay. That's what we're looking for. And 2 squared. So now let's put this into our calculator and then see what we get. Ooh, got my calculator. I'm unprepared, but I have it nearby, so don't worry. So negative 6 plus 4 times 2 divided by 4. And what do we get? We get that it is, we get that this is equal to negative 1 meters per second squared. Okay. Oh. Okay. So what is the acceleration to gravity on the planet? The acceleration 1 meters per second squared. Okay. An astronaut drops an object on the moon. The object falls a distance of 2 meters in the first second. What is the acceleration due to gravity on this moon? So hopefully you're able to do these kind of quickly. So an astronaut drops an object. That drops should give you a hint. Okay, initial velocity is 0. Okay. The object falls a distance of 2 meters. Okay, that means it's going to fall displacement negative 2 meters in the first second. So in 1 second, it falls 2 meters. What is the acceleration due to gravity on this moon? So what is the acceleration of gravity? Again, we have 3 pieces of information and the one we are looking for. And let's figure this out. Displacement of y equals v initial y t plus 1/2 ay t squared. Negative 2 is equal to 0 plus 1/2 ay. That's what we're looking for. 1 squared. So it's going to be 4 divided by 1. So this is going to be negative 4 meters per second squared. 4. Whoops. Hopefully that looks like a 4. Better. Yes. All right. Okay, so this one's going to get a little bit more difficult. A rock is dropped and takes 3 seconds to reach the ground. A second rock is thrown vertically from the same spot and takes 2 seconds to reach the ground. With what velocity was the second rock thrown? Okay, so let's look at this. For this one, since it's a bit difficult, I'm going to kind of draw this out. So we have this one scenario. I'm going to call this scenario A. A rock is dropped, initial velocity 0, and then it's going to take 3 seconds to reach the ground. Time equals 3 seconds. Scenario B, we have a rock is thrown, right? And then it takes a time of 2 seconds to hit the ground. So the question is, with what velocity was the second rock thrown? So we want to find what the initial velocity is of this rock thrown for the B scenario. However, if we look at the B scenario, I'm going to put it all the way up here. We don't know what the initial velocity is. We know the acceleration of gravity on Earth is -10 meters per second squared. We know the time it falls is for 2 seconds, but we only have 2 pieces of information. We don't have enough to find what this is. However, what we want to do now is maybe there's something that A can show us that can help us with finding this initial velocity. So I'm going to put this initial velocity as my unknown. And when I look at the A, so let A here, I have initial velocity is 0. Acceleration of gravity is -10 meters per second squared. And I know it takes 3 seconds to fall. So I have 3 pieces of information here. And let me see if there's something I could find out here, which will give me this here. And what that is they're both going to be falling for the same amount of distance. So this displacement y is something we can figure out. So let's use our formula. Displacement of y, v initial y t plus 1/2 ay t squared. Displacement of y is equal to 0 plus 1/2 -10 3 squared. So this is going to be 90 plus 445, so it's going to be -45 meters. So now I also know that this is a distance of 45 meters. So I can say displacement of y equals -45 meters. Now, let's see if I can find out what this initial velocity is. So, displacement of y equals initial velocity t plus 1/2 ay t squared. So it's going to be -45 is equal to initial velocity t, which is 2, plus 1/2 -10 2 squared. So let's see, this is 4 times 10, that's 40, and then 20. So -45 plus 20, so it's going to be -25 the initial y over 2. So this is going to be around 12.5. If we do the math, it's going to be around -12.5 meters per second. If you use 9.8, you get 12.3. So depending if you use 9.8 or 10, but I use 10, so I know it's going to be 12.3. And we should know it's not going to be upwards. Like this is not correct and this is not correct, because if it takes less time to get here, we should know, okay, it was thrown down and not up. All right, let's look at this. This one's a little bit more challenging as well. To determine the height of a flagpole, someone throws a ball straight up and times it. The person sees the ball reach the top of the pole after 0.5 seconds, and then once again after a total elapsed time of 4.1 seconds. How high is the pole above the point where it was thrown? Okay, so we have a ball, it's thrown. Then we have a pole like this. Okay, what we know is the ball is going to go up and then down like this. And we know the first time it reaches the top of the pole, it took 0.5 seconds. And then we know the second time it reaches the top of the pole, it took a total of 4.1 seconds from the moment it was thrown. And what we're trying to find is how high is this? Okay. So if we're just looking from this point it was thrown up until the 0.5, we're going to be missing something. So let's see what we know from there. So we know it takes 0.5 seconds from the moment it's thrown. We know it's going to be experiencing acceleration of gravity of -10 meters per second squared. And what we're looking for is this displacement. But the problem is we only have 2 pieces of information, so we can't yet find this. So we need to find one more piece of information. There's a few ways of doing this, but what I'm going to try to find out now is I'm going to try to find out how long does it take to get all the way to the top over here, to the highest point. And what I know is from here to here, this is from here to here, it takes a time of a total of 4.1 seconds minus 0.5 seconds. So that's going to be a total time of 3.6 seconds from this starting point to this ending point. So that was 3.6 seconds. So then I know from here to here is going to be half of that. So from here to here is 3.6. That means this is going to be 1.8 seconds. So what I'm going to do is I'm going to try to calculate, I'm going to try to find what this initial velocity is, knowing that from here to here, it took a time of 0.5 plus 1.8, which is going to be equal to 2.3 seconds. I hope that makes sense. Watch it again if it didn't. Okay. And then let's see. So now let me just look at that piece of information. So the total time is 2.3 seconds. Gravity is going to be acting on it, negative 10 meters per second squared. We know also at the very top, the velocity final, I'm going to say, is 0. So now we have 3 pieces of information, and let's find this fourth one, the initial velocity. So I'm going to be using this equation, velocity final is equal to v initial plus at, because that has all 4 of these variables. 0 is equal to v initial plus a, negative 10, t 2.3. And then if I put this in my calculator, I get 23 meters per second. Now I know how fast this ball was thrown. I know that it was initially thrown at a speed of 23 meters per second. So what I could find out next is, now that I have 3 pieces of information, I can find out what this fourth one is. So displacement of y, v initial yt plus 1/2 ay t squared. Displacement of y is equal to 23 t 0.5 plus 1/2 negative 10 t squared. Now let me put this in my calculator. 23 times 0.5 plus 0.5 negative 10.5 squared. What do we get? We get 10.25 meters. Okay. Then we can see it's going to be around 10 meters. Okay. Anything? So anyway, I know this was a harder problem. Remember, in physics, when a problem is very tough, you want to just try to get as much information that you can. The more information that you can get, the clearer the picture is going to get. So even if you're not solving for something immediately, if you solve for something else, like how long it takes to get all the way up here, or the velocity initial, that might give you a clue with how to solve what you're looking for. Okay? All right, let's look at these variables. On Earth, when a person throws a stone vertically upward, it returns to his hand a time t later, capital T. On another planet, he finds that the stone returns to his hand in 2t. In both cases, he throws the stone with the same speed. What is the acceleration of gravity on this planet? So we should know that on this planet, it's going to take longer to get to his hand, meaning the gravity isn't as much. So if the gravity isn't as much, what we know is it's going to take longer to get back. So that being the case, it can't have more gravity. Oh, I guess all the other options are available. Okay. So let's figure this out. What we want to know is we want to kind of be able to visualize everything that's happened. So when he first throws this ball, he throws it with an initial velocity, right? In both cases, even though one takes longer, they throw with the same initial velocity. What we also notice is for both of these, they're both going to be experiencing an acceleration of gravity. Right? Maybe we'll just call that G for this one. And then we don't know what the acceleration of gravity is for this one. So I'm just going to call this a question mark. Another thing that we should know, there's a few ways of doing this problem. But maybe the way that I'm going to do it is that it's going to take a certain amount of time to get to the very top. So I'm going to say this time is equal to t, the top. And then this time over here to get to the very top is going to equal 2t. Okay, it's going to take twice as long to get to the very top. So now we have 3 pieces of information. Oh, no, we just have these 2. Another thing, let's see. What else do we know about this problem? So initial velocity is the same. Acceleration is different. The t is different. And then what is the acceleration of gravity on this planet? That's what we're looking for. Oh, we also know at the very top, the final velocity is 0 for both of these. Final velocity is 0. Maybe I'll make a clear line like this. Okay. So now we want to see, okay, which equation has all 4 of these variables? Okay, there are many questions like this in AP Physics C, so make sure you know how to do these kind of more symbolic problems because there's many questions like this. So it's like, okay, now these 4 variables. So I have, it looks like I could use this equation. VF equals V initial plus AT. So we know in both of these, some things are going to be different. We know the acceleration is going to be different, and then we know that the time is going to be different. So these are the 2 main variables that we're looking for. So we want to know, as time changes, how much is the acceleration going to change by? So we know the final velocity is 0. The initial velocity is the same for both of them. And we want to know how this A changes. I'm going to maybe call this A question mark changes as this T changes. So what I'm going to do is I'm going to try to isolate this. I'm going to try to isolate this acceleration. So I know that I'm going to put this V initial on the other side. And then I'm going to put this acceleration. We're going to call this gravity. And then we have T on this side. And what I should know at this point is if T changes by a factor of 2, that means this gravity here has to also change by a factor of 1/2. Okay? So if this T changes by a factor of 2, that means this side over here needs to change, and that needs to change by a factor of 1/2 so that both these sides change by a factor of 2. I hope that makes sense, which would mean this D is correct. I'm going to show another example of this, but if that didn't make sense, please watch it again, okay? Because there's a lot of questions like this in AP Physics. So let's look at this one. Stone A is dropped from a height h, and stone B is dropped from a height 2h. If stone A takes time t to reach the ground, stone B will take blank. Okay, so let's look at this. A, and then this is dropped, and then it falls a height of h, and then we know it falls at a time t. B, we know this is going to be twice as high, so this is 2h. A rock is dropped, and then we're looking for what is the time going to be if this changes by a factor of 2. So let's look at the main formulas we have. So we know that the initial velocity is going to be 0. We know the time it takes to hit the ground is going to be a t. We're just going to put t. And we know the displacement in the y, we call it negative h. We also know, sorry. So we're looking, sorry. So we're looking for what time is as the displacement changes, right? What we should also know is the acceleration of gravity is the same. It's going to be gravity for both because we're both on Earth. It doesn't say we're not on Earth, so that's how we got it. So now let's try to, okay, these are the 4 formulas we're going to use. We're trying to find what time is in reference to the displacement. So let's look at the formula we need. So we see that this formula has all 4 of these. And let's try to simplify it as we can. Displacement in the y. So that's what we're looking for. We know that this is going to be h, right? So it's going to be falling down a distance of h. We know the initial velocity, they're both dropped. So this is going to be 0 plus 1/2. And this is going to be gravity, right? So it's going to be negative g and then t squared. So what we want to know is as this h changes, how is t going to change? So I'm going to put everything onto one side except the t. So this is going to be simplified to be, if I'm going to bring this over, it's going to be 2h or negative 2h over negative g, the negatives cancel out, is equal to t squared. And now what I want to know is, as h changes, how is t going to change? So let's say h changes by a factor of 2. That means t needs to change by a factor of square root of 2, so that both these sides are going to be changing by a factor of 2. Okay? So now it's going to have square root of 2. Like that. Okay, hope that makes sense. If not, watch it back, because students a lot of times have trouble with these, but there are so many questions like this on the AP Physics exam. Okay, last question. You drop a penny, and after it travels 4 meters, you drop another penny. What happens to the distance of the pennies from one another? Okay, so it seems like this is a question similar to one that we've seen before. So you drop 1 penny, and then, so the 1 penny's dropped, and then 1 second later, or 4 meters after it has gone down, you drop another penny. So what we should know is, last time we learned that this penny here is always going to be faster than this penny. Always faster. Okay? And this one is going to be always slower. Why? Because since they're both accelerating, but this one started its acceleration first, that means it's always going to be faster, right? Gravity has been pulling on it for a longer time, so it has been accelerating for a longer time period than this one. So if this one's always going to be faster, that means that this one is always going to be getting further and further away from this. If you can imagine in a race, if somebody's always faster than you, they're going to be getting further and further away from you. So what happens to the distance of the penny from each other? It increases. And I hope that makes sense. Watch it again if it doesn't make sense. But the distance between them is always going to increase, because the penny that was dropped first is always going to be faster than this penny afterwards. Okay? They're both going to be getting faster and faster, but this one's always going to be faster than this one. Alright guys, thank you for watching, and we're going to be doing graphs for the next one.